Alright, chapter 13.5, heat transfer. Alright, introduction. Heat transfer energy transit, which occurs with the result of the temperature gradient difference, or difference. The temperature difference is thought of as the driving force. The cause of the heat energy flow. The heat transfer occurs with three basic mechanisms or modes: conduction, convection, and radiation. Conduction heat transfer is defined as a heat transfer of solid fluids without bulk motion, as shown in Figure 13.25. Heat conduction generally takes place in solids. In fluids, conduction is due to collisions of the molecules during the rate of motion. Solids due to the combination of the vibrational molecules, the lattice energy transport free electrons. Observe the rate of heat conduction throughout the wall. The constant thickness of the proportional temperature affects difference temperature 2 over temperature 1 between the surface and normal of the heat flow. A direction inversely proportional to the thickness of the wall L. In other words, conduction through the heat of the wall is equal to the thermal conductivity of the wall material times the cross-sectional of the area of the wall times the surface temperatures of the wall over derivative x. And then composite wall material series, shown composite wall, three different material, different thicknesses. Heat transfer rate 1, 2, and 3. Convection is the mode of the heat transfer between solid surface and the adjacent fluid with motion involved with the combined effects of the conduction fluid motion, faster fluid motion, greater convection, heat transfer in absence of any bulk fluid motion. The transfer between the solid surface and the adjacent fluid is pure conduction. Present of bulk motion fluid enhanced with the heat transfer between solid surfaces and fluids. Convection is called the forced convection if the force flowed through the flow over the surface external means of the fan pump the wind. In contrast, convection is natural free convection if the fluid is caused by the buoyancy force that is induced by the density of the difference due to the variation of the temperature of the fluid. Heat transfer as a solid surface can be obtained. Convection heat transfer coefficient funds Reynolds number. The more turbulent flow, the higher the convection heat transfer coefficient will be, where H is convenient with the heat transfer component, A is the transfer area, the T is the surface transfer of the wall, and T infinite of the bulk fluid temperature. R is equal to 1 over HA over HA. Alright, radiation is the energy emitted by the matter form of the electronic wave as the result of the change of the electronic configuration of atoms and molecules. Unlike conduction and convection transfer, the energy radiation does not require the presence of the intervening medium. In fact, energy transfer of the radiation is the fastest speed of light, and it doesn't suffer no attention actuation in vacuum. Exactly how energy sun reaches the Earth. Maximum rate of radiation which can be emitted to the surface, the absolute temperature, is given by the Stauffen-Boltzmann law. Where Stauffen-Boltzmann constant and emissivity of the surface, the idealized surface to emit and radiation maximum rate, e to the 1, known as the black body of the radiation emitted by the actual surface, less of the emitted with the black body. The value of the range of the 0 to the emissivity of the radiation is less than 1, measures how closely the surface approaches black body. From small body to the small compared to the surrounding, the net rate with the relative heat transfer body is q to the 12. The other important radiation property, surface absorptivity, which is the friction of the radiation energy incident with the surface of the body of the surface of the list, like emissive, the value of the range is 0, greater than absorptivity less than 1. Black body observe the entire radiation incident on it. The black body is a perfect absorber at 1, as well as perfect emitter with the practice of the absorption and emittivity are assumed that independent with the temperature of the wavelength of the radiation. Average absorptivity of the surface is taken an equal average emission. Figure 1329 shows incidental reflected absorbed energy on the surface. The rate of the surface absorption radiation is determined from the the rate at which radiation incident of the surface of the non-transparent surface of the portion of the incident radiation not absorbed of the surface of the reflected surroundings. Difference between rates of radiation emitted with the surface of radiation absorbed with the net radiative with the heat transfer. The rate of radiativity absorption is greater than the rate of radiativity emission, and surface is said to be gaining energy with the radiation. Otherwise, surface is said to be losing energy radiation. Real bodies frequently approximately gray body, which is one known as a proximity to emissivity. Alright, the general conduction equation based on Cartesian coordinates will be the first law of thermodynamics. Rate of energy conducted with the control volume plus the rate of energy generated in the control volume equals rate of energy conducted with the control volume rated energy in the inside of the control volume. By combining these equations, each of the rate, the heat generated rate, unit volume of the approximation is called the thermal diffusivity of the material. The thermal conductivity represents the well material conducts heat, and it has heat capacity represents how much energy material stores per unit volume. Larger the diffusion, the faster propagation heat into the maximum medium. Small value of thermal diffusivity means the heat is mostly observed with the material with a small amount of the heat will be conducted after further. Energy is generated in some cases, such as nuclear reactors, which in this term is energy produced, appears in section equation 13.5. Plane wall internal heated. Figure 1330 shows a plane wall with the internal energy per unit volume. The heat source of the center plate with respect to the temperature profile symmetrically about center. For this case, process is stated one-dimensional heat flow. Therefore, equation 116 simplified as to which can be solved. The general solution is cylindrical internal heat generation. Figure 1331 shows a solid cylinder internal heat per unit of volume. Example: the system with tungstens in an electrical light bulb. Electrical heating temperature for the case of the system steady state where the temperature varies within the radius. Using procedures similar to the plane with the example, we get the temperature profile of the achieved the solving above the equation subject to the boundary condition. Heat transfers from an extended source. Extended surface. Purpose of adding an extended surface to help dissipate with the fins are usually add with the heat transfer to the device, increase the rate of thermal removal. Because of the increase in the heat transfer area figure for straight fins shown in figure 1332. Total dissipated heat can be calculated with the following equation relation with the H of the convection heat transfer coefficient is exposed with the parameter K is thermal conductivity AC. Cross-sectional energy, TW, temperature at the base, at the fin, T, infinite fluid temperature, and M over square root of HP over the KAC, and LC and L and plus ACP is corrected with the length of the fin cross-sectional area length. LC is equal to L. Unsteady heat conduction. Here we consider the transit conduction problems which are with no internal heat generation. Temporary will therefore vary location system with time. Temperature and heat transfer variation systems are dependent on internal resistance and surface resistance. If we have a slab at an internal temperature of this fluid stream, heat is transferred the convection of the surface over the temperature of the degree of the transfer of the center of the slab, the surface of the fluid. Now, if the system is copper, the volume is small. Temperature response within a small slab considerably different with the glass and volume is large. Response as to how do we do the internal resistance of the material further in convection coefficient is very high. The surface temperature becomes also almost identical with the fluid temperature quickly. Alternatively, a low convection sufficient large temperature difference exists between the surface and fluid. The value of the convection coefficient control what is known as the surface resistance heat transfer. Temperature variation with the system dependent on the internal surface resistance, the large internal resistance of the smaller the surface resistance, of the larger temperature variation of the system, vice versa. The Biot number is defined as convection of the surface within the body over the conduction within the body. System and negligible internal resistance lumped capacity method. Your Biot number is less than a tenth. The temperature profile within the body is quite uniform. Rate of charge, internal energy of the body is equal to the rate of the heat taken away from the source of the convection. Solve an equation temperature variation with the time and the total heat transferred up to the time is, and radiation view factors equation with a black body with a gray body's equation with a 13, 133, 114. Assume small bodies could see the only large enclosed body, nothing else. Hence, all radiation leaving the small body would reach the large body. For each case, if the two objects can see just more than just one each other, the one most introducing to the view the factor F, heat transfer calculations between significantly more involved. The view of the F13 or 12 is used as a parameterized fraction. Thermal power leaving object 1 and reaction reaching object 2, specifically quantity is equal to. Likewise, fraction thermal power leaving object 2 reaching object 1 is given. The cause of the two black bodies in thermal equilibrium can be derived with the following reciprocity relationship. The view factors A1 F12 is equal to A2 F21. The once known F12 and F21 can be calculated immediately. Radiation view factors analytically derived with simple geometrics. Heat transfer between two finite gray bodies. Heat flow transferred from the object 1, object 2, but the two objects only as fraction each for the other. Nothing else is given. Equation demonstrate the use of the F12, but in representative of the non-physical case, it would be impossible to position two finite objects such as these, such that they could see only proportionate to each other and nothing else. On the contrary, complementary view of the fact 1 to the F to the F12 cannot be neglected. Radiation energy sent in those directions must be accounted for in thermal bottom line. Alright, heat exchangers. Heat exchangers between two fluids of different temperature separated by a solid body of wall occurs in many engineering applications. The device used to implement the exchange to achieve the heat exchanger. Specific application may be found in space heating and air conditioning. Heat exchangers typically classified according to flow arrangement type of the construction. Figure 1334 shows the two simple parallel flow and counter heat exchangers. The rate of heat exchange is Q, which between the two fluid systems, the heat exchanger is shown in the figure. UA value and LMTD, unit overall conductancy of the UA value, defined as a product overall heat transfer coefficient, transfer area, counter flow application heat transfer rate, to define the product overall conductancy, long mean temperature difference. Shows the long mean temperature difference is equal to temperature resultant out and temperature in over in, and temperature times temperature out over temperature in. That goes in example 13. An efficiency, heat exchanger efficiency is defined as ratio of the heat transfer, the exchange over the Q, the maximum theoretical rate of the transfer, and EQ over the Q max. Maximum theoretical rate of the heat transfer limited by fluid stream of the smallest heat capacity rate, where it is smaller, and number of transfer units indicated the actual heat transfer area. Physical size of the heat exchanger, the larger value of the number of transfer units, the closer the unit is thermodynamic limit. It is defined as normal number of transfers overall on units overall conductancy over the maximum theoretical rate of heat transfer. 13.6 Summary. Fundamentals general thermodynamics have been presented. System closed open. The property of the intensive, the extensive state interaction process, reversible or reversible, have been defined. Energy exergery, available energy, entropy have been defined by work heat interactions have been discussed early. Balance equation for mass, entropy, and energy exergy have been developed. First and second law of thermodynamics has been presented. Properties of ideal, non-ideal gases have been calculated. Any conversion devices such as nozzle, diffuser, turbine, pump, compressor, boiler, condenser, evaporator, heat exchanger have been analyzed. Thermodynamic cycles such as the Carnot cycle, the Ransing cycle, vapor compression of refrigeration, heat pump cycle, Otto cycle, Branton cycle have been discussed in detail. Combustion process has been reviewed. Heat transfer interaction has been presented along three modes of conduction, convention, radiation. One-dimensional heat transfer through the slab, composite wall, circular duct have been analyzed. Force natural convention have been reviewed. Convective heat transfer coefficient, different conditions have been calculated. Thermal analysis have been developed for the system both in steady state conditions as well as unsteady state conditions. Fins heat exchangers have been reviewed. Then it goes into some tables. Superheated steam table. More tables. Practice problems. Chapter 14, Biology.